Today's lecture is about a pretty classical topic in complexity, circuit complexity. It's Razborov and Smolensky's lower bounds for AC0 circuits with mod P gates. So about 4 lectures ago, when we started talking about circuit lower bounds, we proved another famous lower bound due to Hostad about AC0 circuits' inability to compute parity. So we showed the depth D circuits for the parity function, the mod 2 sum of the bits, require very large size, exponential in n to a power depending on d, and it's even the best possible power, which is n to the 1 over d minus 1. Okay, so people were pretty pleased with themselves when that got proved in 1986, and they thought, all right, let's keep going, let's make it better. There's a couple of questions you could now imagine. One question you could ask yourself is like, well, what if we take constant depth circuits but allow parity gates? So what if we allow parity gates? Which is actually pretty natural because these circuits were and or and not. Like you chose like a subset of all the 2-bit functions. Like why not choose that? Allow yourself that last 2-bit function, parity of 2 bits. And since we're doing constant depth circuits, I guess we should allow like unbounded fan-in parity. And now once you allow a parity gate, well, of course, you can compute parity with a size 1 circuit. So it'd be cool to get a lower bound for this class if you could. And Razborov did in 87. And he showed that some other symmetric function, in fact, a very simple one, the majority function, requires, and, or, not, and parity circuits. Oh, I should add in here depth D. Parity circuits, that's a terrible circuit of size, well, almost as good. 2 to the omega n to the 1 over 2d. Okay, so slightly worse exponent, but basically it's exponential in a power of n. So that's pretty satisfying. And then another question you could ask is, well, what if we stick with lower bounds for the parity function, but allow ourselves, that's the mod 2 function. What if we allow ourselves mod 3 gates? So slightly converse question. What about computing the mod 2 function parity of arity n using mod 3 gates, and of course and or not. So here, of course, having mod 2 gates helps you compute the mod 2 function on n bits, but perhaps it's not so helpful to have the mod 3 gates. I should say what exactly I mean by this. So a mod m gate, taking W input bits, well, it just sums them up mod m, but then it's still supposed to output 0 or 1. So the traditional way to have it is, this is 0 if the sum over I of xi is 0 mod m, and you output 1 if it's non-zero mod m. Okay, so this question was kind of natural. People are exploring the ability of constant depth circuits to count and to commute symmetric functions, all these things, mod 2, mod 3, majority all like symmetric functions of the inputs. And for this question, it was answered shortly thereafter by Smolensky, also in 87, using similar techniques. And this is something we'll also prove today. It'll basically be the goal of today's lecture. To answer this question too, again, for depth D, the same size bound is needed. Size 2 to the omega n to the 1 over 2d is required. And if you're not too concerned about whether this is 1 over 2d or 1 over d minus 1, as long as it's some constant power when d is a constant, this gives a totally different proof of Hostad's result. In some sense, a better one because, like, you're allowed not only AND, OR, and NOT gates, but you also allowed mod 3 gates. And this proof is actually easier, honestly. So except for this feature, it's like an easier and in some sense better proof. Well, Hostad's proof also has its merits. It has the ability to like show that like the parity is not even like approximately computable by a constant depth circuit, which this argument won't. But if you just want the shortest route to parity not being in AC0, it's probably via this method. This is a different proof of Hostad's result. So that's nice. And in fact, he proves something, Smolensky proves something a little bit more general than this. So this was about allowing mod 3 gates, but you could imagine allowing counting gates modulo any number. So let's make a little bit of notation here. This complexity class AC0 brackets M is the function's computable by constant depth, poly size circuits with unbounded fan-in and or not and mod M gates. Okay, so these are gates that can be do a little bit of counting. And what Smolensky more generally showed is that for all primes P and Q distinct, the n-bit mod P function is not in AC0s with mod Q gates. Okay, and in fact, exactly this size trade-off. If you treat P and Q as constants, the n-bit mod P function requires this size circuits with mod Q gates. So all the results on the board, Smolensky's more general result, Razborov's result, they're all basically proved in the same way, just very slight variations. So, for today I picked, this specific one about computing the parity function, the mod 2 function, with mod 3 gates.
Is this still true if you allow like all mod Q gates not equal to P?
No. Well, I mean, presumably yes, but we don't know how to prove it.
We don't, because I guess you can do mod M gates for confidence. Okay.
Yeah, I didn't actually double check this, but I'm 95% sure that it's true more generally if these are, coprime prime powers. So as we'll see, what we really need here, in attacking AC0 with mod Q gates is that there's a field of size Q. Yeah?
I'm curious, in the development here, have people looked into what happens if you allow like a majority gate?
That's a good question. So if you allow majority gates, this is basically stronger than allowing, if you allow yourself majority gates of unbounded fan-in, then you can basically not even worry about having ANDs and OR gates, because we kind of assume that like plugging in a 1 or a 0 is sort of free, and so you can make an AND gate out of a majority gate by plugging in a bunch of maybe 1s or 0s appropriately. Yeah, so people talk about constant depth circuits with majority gates only, which is sort of without loss of generality. That complexity class is called TC0, T for threshold. And it's even harder to prove lower bounds against. For example, we don't have any lower bounds against depth 3 TC0 circuits. And actually, if you allow like not just majority gates, but like weighted majority gates, so like instead of looking at whether sum of xi is bigger than n over 2, you look at sum of wi xi is bigger than some threshold where you can choose different wi's. Then we don't even know circuit lower bounds for depth 2 circuits of this class. So for all we know, SAC can be computed by such circuits. Yeah, so that's actually sort of bumping up. It's a good question because these are all like, well, what if we give ourselves like the power of basically various symmetric gates? Gates that only depend on the number of ones coming in. And if the function is like mod a prime, then we know what to do. But like majority, we're in trouble. So this is really exactly like bumping up against, and I mentioned this just now, like our ability to prove any circuit lower bounds. Like these, AC0 for, is something we can kind of handle, and we can like squeak it up to like AC0 like with mod of prime gates. That's basically the most expressive class of circuits that we can prove lower bounds against. So for example, this is a remark, which we'll come back to later. There's no known language, like explicit language. That usually means a language in NP, such that we know how to prove that L is not in AC0 with mod 6 gates. Which, by the way, is the same thing as AC0 when you allow mod 2 gates and mod 3 gates. So I'll let you think about why these are equivalent. It's quite trivial. It's because like 6, there's no field of size 6. So that just shows a little bit the state of embarrassment for circuit lower bounds. Yeah?
Don't we know like a language in Next that's not in? Yeah.
Yeah, I'll mention that. So let me just say first that like it's conjectured that the majority function, which is in L, is not commutable with constant depth poly-size circuits with mod 6 gates, but we don't know how to prove that. As Nick pointed out, so I mean like this was like, I don't know, the state of affairs since 1987. And in fact, like it was so like embarrassing that like until 2011, we didn't even know this, which is ridiculous. I mean, this is hardly even considered like an explicit language, but we didn't know this. And then like in 2011, Ryan Williams managed to find such a language, and we'll do that proof by the end of this course. It's kind of funny though, because it's like just squeaking up to the place where we have kind of trivial circuit lower bounds. If you go up to MA-exp, which is like, it's to MA as, is to MA as exp is to P. So it's like, Merlin-Arthur gains where Arthur is allowed exponential time. Then we know an explicit language in here, we know a language in here that doesn't have circuits of any kind of circuits of any polynomial size. And that's just like a scaling up of a theorem that we already know, that there are languages in MA that don't have circuits of any fixed polynomial size, like n to the 100. And that's like not such a hard result. So like this class is sort of in some sense barely below this class, and like this is our amazing like result like 25 years after Smolensky. Okay, so let me erase this because it's currently wrong, but I can put this back. Okay, any questions? Any more questions? Okay, so I'm going to tell you our latest and greatest in circuit lower bounds for explicit languages. And let me just summarize the basic idea, and you'll see a little bit why this primes and fields come up. The idea is to show that if you have a depth D, size S, let's say mod 3 circuit, and of course by that I mean mod 3 gates of unbounded Fanon, but also and OR gates and NOT gates, then we're always going to be looking at sort of approximately computing it by some simpler thing. We'll show it's approximately computable by an F3 polynomial. Okay, so an n-variate polynomial with coefficients in the field of size 3, very small degree. So log s to the d degree. Okay, so think of s as something super polynomial, but then this is still like, only polylog maybe. D is a constant. So this is like, much, much less than n, unless s is exponential. And, that'll be the first thing we'll prove. And then there's like a second thing to show that like, well, it's very unlikely that this complicated function, in some sense parity, is computed by a very low degree polynomial like this. Okay, so that's like a separate counting argument that's not too hard to show. Okay, so that's actually basically the plan for the day, is to put these ideas into practice. I'm going to make the proof of this idea like very slightly more complicated than it needs to be, because it'll help us when we're studying, well, constant depth mod circuits later. Okay, so let me make a couple definitions. a polynomial P, let me just focus on F3. F3, this is the field of size 3, by the way, is, let me just call it proper. It's not really a real term, but it's suitable for just today's lecture. If its output is in 0, 1, whenever its input is. So it'll just be convenient to have this term because we'll often be studying polynomials with the property that, although they take as inputs, 0, 1, 2, and may output 0, 1, 2, we're going to be studying ones which have the special property that if you only give them 0, 1 inputs, they happen to give 0, 1 outputs. And then this is another important concept. It's actually a bit of a vague definition, but we'll say a randomized polynomial P of x comma r is, well, let me say it vaguely. What I mean is we think of x as being like the real input and r as some random bits. I hope you'll figure out what I mean by this as we go along. Oops. So basically what we're going to do, to prove this, to make concrete this idea is we're going to try to approximate, a mod 3 circuit by a low degree polynomial P. And what we're going to mean by approximate is actually we'll sort of approximate it by a polynomial P with low degree polynomial with two kinds of inputs, x and r. And it'll have the property that for every input x, if these r bits are chosen uniformly at random, then the output of the polynomial is correct with high probability for x. Okay, and we won't worry, about the number of random bits that are used, although eventually we'll show that it can be small. Yeah, we just want to show that for all inputs x, when these guys are chosen at random, it gives the correct answer with high probability. Any questions? Yeah.
Is P, is the domain P to the 1 to the n, or F3?
It's actually going to be F3 to the n. Yeah.
So when you say the correct output is correct output with respect to original P? Or?
There is no original P. A correct output with respect to the circuit that we're approximating.
So the randomized polynomial is defined with respect to the circuit.
Yeah. Let me just, maybe it'll become clearer once I state the theorem that we're going to prove. Okay, so we're going to prove two theorems today. Theorem 1 is let f be any Boolean function that's computable, apostrophized one letter, that's not very worth it, by depth d, size s, and or not and mod 3 circuit. Okay, then there exists, proper randomized polynomial P over F3. Answers one question. Such that the degree is not that large. So the degree of P is at most 2 times t to the d. Okay, so really it's for all t greater than 1. That's a parameter you get to choose. And for all inputs x, the probability when you choose r at random that f of x, well, let me write it this way, that p of x r differs from f of x is at most s times 2 to the minus t. Okay, so we're going to take this parameter t to be something like a little bit bigger than log s. So this will become small. And then the degree will be like, order log s to the d. OK, so we're going to convert the circuit into a low-degree polynomial, which actually has the property that it kind of, like a BPP-style property where, like, for every input, the polynomial in some sense computes the right answer with high probability when its other bits are chosen at random. Yep.
Just to clarify, when you say the degree of the polynomial, you mean like for example, a multilinear polynomial could also have high degree, right?
Yes. I also mean that another thing you might have asked is like it includes both degree in x and in r.
Yeah.
Yeah. So if it's over f3, then there's no point in ever cubing or higher a variable. You may as well just have like a most quadratic in all the variables. But there are, well, even in x, there are already n variables. So the degree could be as high as 2n, and then that's not even including the degree in r.
Like if you're only caring about proper polynomials, you don't even need to square it then.
That's true. Yeah. Let me just mention that this is like a bit specific to mod 3. I just decided to write that to keep it simple. But this theorem is like perfectly equally true whenever 3 is replaced by a prime. So if this is q, then you'll get like a factor. This 2 will become q minus 1. And this will, you can leave this as 2 to the minus t. Or if you want to get something even stronger, it can be actually q to the minus t. But then you really need to let r range in fq to the n. Yeah, that's not a big deal. I mean, one should think of q as like an absolute constant. Like it's going to be 3 or 2 or 6, 5 or something. So basically, everything is like a constant. But you'll see as we do the proof that it doesn't really depend on the number 3, except insofar as 3 is a prime.
All primes.
Yeah. Let me just double check everything. You might have to work harder if it's a power of a prime. I mean, there's going to be one step where we use Fermat's little theorem, and then I'll have to think about it. Yeah. Yep.
What's the t?
Oh, t is a user-selected parameter. We're going to select it to be like log s. OK. And let me just do a quick corollary of this. In fact, setting the parameter. Actually, before I do that, I also want to do, for corollary purposes, like a little twist here. I want to get a polynomial that doesn't have any random bits that just gets the right answer on most x. Here we have a polynomial that gets the right answer on all x with high probability. I want to switch it to most x. So see, this implies that, of course, if I pick x also at random, then this is still equally small. I mean, it's true for every x, so it's true if I pick it at random. OK, and then this is the same as the expectation over r of the probability over x of this. OK, so if this quantity in expectation is at most this small number, then therefore there exists an r such that it's small. OK, and then we can sort of just like think of this as like, I mean, r is now sort of fixed. We can think of this as like p sub r of x. OK, so we've got just one polynomial that gets it right on almost all inputs. OK, so a little conclusion that we can get is, okay, this is getting a little messy. Sorry about that. But again, by also taking t to be order log s, we finally conclude, let me write it again, that there exists a proper polynomial f, p. Maybe it's p sub r, but anyway, p of degree at most order log s to the d, such that, let me write it the other way, the probability over random x that p of x equals f of x is greater than or equal to, I don't know, 0.999. Okay, so this is the corollary that I want you to take away from this theorem statement. And then, I guess that's the manifestation of that idea there. So we're going to spend half an hour proving that. And then after that, we're going to prove theorem 2 for the class, which is quite simple. It's just that there does not exist a polynomial p of degree at most square root n such that this polynomial p agrees with parity on 99% of inputs. It's also known as mod 2. Okay, so if it's saying in other words, if you want some polynomial, even over f3, that like computes the parity, not everywhere, but even on like 99% of inputs, then it better have degree at least root n. This is going to be a counting argument that's not too hard. Okay, and what's the final conclusion? By putting theorem 2 and the corollary together, well, it's that if a depth d, size s, mod 3 circuit computes parity, then we need that order log s to the d is at least root n. Okay, and I take 1 over dth power, I get 1 over 2d here, I exponentiate, so that's okay, which was the desired conclusion. The size has to be exponential and n to the 1 over 2d. Okay, so for the rest of the class, I'll prove theorem 1 and theorem 2. And theorem 1 is sort of like the one of more main interest for complexity theory. I mean, it'll come up, this idea of approximating constant depth circuits with mod gates by polynomials will come up again in complexity theory. Theorem 2 is just it's a fact about life. Okay. Well, let's do theorem 1. You might not be surprised to learn that we're going to do it by some kind of gate-by-gate replacement. We'll take the circuit and replace each gate by a randomized polynomial and get a randomized polynomial for the whole circuit. So let me, I guess, start it over here. Okay, so we want to go through all the gates and convert it to a gate to a polynomial, I guess a randomized polynomial, and we want to keep the degree low, and we want to keep the accuracy high, and also we have to maintain that it's a proper polynomial. So let me just state the construction, and we'll analyze the error and the degree at the end. Okay, so the input gates xi, well, we just replace them by the polynomial xi. Okay, and that's proper, because if this is 0 or 1, then this is 0 or 1, and the degree is 1, which is awesome, and there's no error. So think of this as like a randomized polynomial that doesn't even have any random bits. I mean, it has 100% accuracy. So that's easy. The other super duper easy one are the NOT gates. I know you can tell what to do here. If you have a NOT gate and you have some randomized polynomial that you've concocted for its input, then what should you put here? Well, you just put 1 minus that. And that's proper. And also the degree and the error are actually unchanged. But I mean, for the AND and OR gates, I'll just check the properness and like I'll leave the degree and error business for the final analysis. But that was so easy that I'll leave it like that. Oh, and the mod 3 gates, of course. That's another classic gate. Let's see. OK, I'm going to erase these 2 boards. OK, so actually the mod 3 gates are pretty easy. They're actually not the hard part, luckily, since our polynomials themselves are like operating over F3. It's going to make it easy. So we have some mod 3 gate here, like many inputs. And inductively, we've replaced these all by some randomized polynomials. And if you remember, this is supposed to output 0 if the sum of these things is 0 mod 3. Otherwise, it's supposed to output 1. So we can start by doing this. It looks good so far. The degree has not really increased. Well, trouble though is this is not quite proper. If all the p's are outputting 0, then this is 0, which is thumbs up. But if all the p's are, well, if the sum is non-zero, in other words, it's 1 or 2, well, this could be like 1 or 2, but it's supposed to just be 1. OK, no problem. We square it. OK, so mod 3, 1 squared is 1, and also 2 squared is 1. So that's convenient. In general, remember I said this doesn't really rely too much on properties of 3. In general, if this is an FQ, you make this power q minus 1. OK, and then Fermat's little theorem tells you that 0 squared is 0, but anything that's not 0 when raised to the power of q minus 1 is 1. OK, and that's not very, I mean, again, when you think of q as a constant, like this is not like a big deal. It's not going to be a big deal from the point of view of degree. So, what's that?
There is nothing different if you take a 9.
Yes, my number theory is weak. Is that true? It's like.
Yeah, because you have the Euler's theorem. Like if you raise to the power of 5 of that, and
That's only
no,
true
but like
if
it's not
co-prime.
true. Like you know that it's
only
not
true
true
if
because
it's
it's
co-prime,
0.
yeah.
Then again.
It's only true if it's co-prime to n.
I mean, are you relying on it being a prime power?
Yeah, so if you have n and you try to raise it to pi and that's co-prime and then you're in trouble.
Oh, you want 0 and like all non-zero.
Yeah, so this is where like it goes wrong if you're like working at least, I mean, let me not worry about prime powers, but let's take 6, the least thing which is not a prime power even. That's where it goes wrong. I mean, like this could like add up to 1, 2, 3, 4, or 5, and you want to like convert it to 1.
Could it work if I
Yeah, wait, that doesn't seem so bad. What's that?
4 if you try to get it to 1, it's not possible.
Yeah, I mean, yeah.
You could put like a more complicated polynomial than just like something squared, but it's not clear what that would.
Yeah, that's what I was thinking. Like, what's wrong with that?
Well, you can't have constant term, I guess. Because then zeros won't get back to 0.
Yeah. OK, yeah, one should think about that.
If you define a polynomial, what's in terms of I want 0 only if it's 0 and 1 otherwise? If you define 0 if it's like not coprime and 1 if it's coprime, is it a good polynomial like in general or not to work with? The original definition.
Yeah, that might be this. You're asking about changing the definition of a mod gate.
Yes. Yes.
Yeah, so I mean, like, you want to like look mod 6 and see if like it's 0 if it's 0, 2, 3, 4, or like 1 if it's 1 or 5.
Yeah.
Yeah, is that?
You're doing a good thing, like, yeah.
Yeah, you can invent that. I mean, I guess so. Yeah, I have to think about like if that's like. I was just trying to think if that's like reducible to like some other case that we know. I don't know. You can think about that. I mean, first you can think about like why having mod 2 and mod 3 gates is the same as having mod 6 gates. And then once you complete that exercise, think about your funky gate and see how it fits into the picture. Okay, good. So this is, thanks to Fermat's little theorem, is proper. And I'll analyze the degrees and stuff in a second and the error, but basically everything is great here. Like, if these guys didn't have error, then we're not introducing any error, and the degree went only up by a factor of 2, which is fine because the circuit has constant depth. Okay, so the main part of interest is the OR gates. And as usual, I'll only treat the OR gates and not the NOT gates because, I mean, the OR gates are like, by De Morgan's law, it's kind of the same as AND gates if you throw in NOTs appropriately. But like NOTs are like a dream. Like nothing happens with NOTs. It's just 1 minus the thing. So I assure you the analysis is the same. OK, so again, let's imagine we have this scenario. And we want to like have some input polynomials p that we've constructed already. And we want to like concoct an output polynomial g. OK, so the obvious first thing to try is just literally do it, right? So you could go for this polynomial. OK, and that would be great. It would exactly compute the OR. But the problem is this has terrible degree. So, I mean, this fan-in, the only way we can bound it actually is by s. OK, so the degree here could be as large as gaining a factor of s, which is a disaster. So we don't want to do that. So this is, of course, where the error is going to come in. And basically, we use the same idea that we used in like the Valiant-Vazirani proof from so long ago. I mean, it's to like approximately compute an OR by like summing up a random subset of the inputs. It's a classic trick. So here's what we'll do. We're going to introduce some new random bits. OK, so these like are new r's that are going to go into G. And we're going to think of them as random and 0, 1. It would also be fine if they're random in like F3, but like let me just, so I don't have to worry about the meaning of proper, let's just let them be random in 0, 1. And we're going to simply, OK, this is not the final solution, but for a second, let's just do this. Let's imagine that G is just this, P1 R1 plus dot 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 plus PW RW. Okay, it's like a random sum of them. As always, let's square it so that we can convert zeros to zeros and non-zeros to ones. OK, so let's take a look at this. First of all, it's proper, which is nice. This sum is done mod 3 down here, by the way. OK, so you're summing up basically a random subset of the p's and squaring. And just towards correctness or approximate correctness, note that if like all the p's are outputting 0, then this thing is outputting 0, which is good. That's what an OR gate is supposed to do. OK, and on the other hand, if at least one of the inputs is 1, say without loss of generality that it's the first one. Then we're going to do like a simple analysis that I guess we've seen before. It's like Valiant-Vazirani. Just like imagine we choose, I mean mentally, we choose R2 through RW first. OK. OK, so then like we have P1 up here inside the square. We have this. So imagine like p's are all sort of fixed. At least one of them, well, in particular, without loss of generality, this one is like a non-zero element of F3. And just imagine we choose R2 through RW at random, and we don't even care what happens. This will come out to some quantity, theta, in F3. And now we're adding in, well, with 50% chance, we add in P1, which is a non-zero value. And with 50% chance, we add in nothing. OK, so this whole thing is, it's equal to theta with probability 1/2 and theta plus p1 with probability 1/2. And at most, one of these two numbers is equal to 0. Actually, it could be that neither of them is equal to 0. Maybe like this is 1 and this is 2, or vice versa. But in any case, they can't both be 0 because p1 is not 0. So therefore, this is equal to 0 with probability at most 1/2, which is great. So in some sense, the probability over R that like G, this temporary G is wrong, if you will, is at most 1/2. Yep.
So it doesn't depend on the probability that the P sub 1, P sub W?
Yeah, I'm going to do that more carefully in a second. But I guess what I mean by that is like, if you treat the values of P1 and PW as, you're agnostic to whether they're right or wrong. You're just like, well, P1 through PW are like whatever they are. I'm now going to ask myself, like, what's the chance that I correctly compute the OR of like these guys? That's all I'm analyzing here. Yeah, I didn't make that super clear. So, good question. OK, so there's one more obvious idea, right? I mean, this is not such a great error bound, but if you look at the statement of the theorem, s times 2 to the minus t, I think you'll hopefully see what we should do. So like the actual G, it's just choose t independent such R vectors and multiply them together. The G's together. Okay, I didn't write that extremely properly, but I hope you see what I mean. Okay, so you'll actually have t times w random bits. Okay, and therefore, for this final G, the probability that's wrong is at most 2 to the minus t. In the sense that the probability that it incorrectly computes the OR of P1 through PW, whatever that is. OK, so that's the construction of the polynomial, the randomized polynomial. And now we'll just check that it has the desired degree and error bounds. Yes?
Wait, I think I haven't been paying close attention. But like, wait, if you multiply all these together, if only one of them is 0, then the whole thing up is 0. So you're wrong in that case.
Oh.
It would be like you're doing AND or something. But
Oh, yeah, maybe I'm doing, OK. I guess you want to do this thing, right?
yeah, you want to do that next thing.
Yeah, thanks. I did that a little too fast. Don't multiply them together. Let's do, thank you, do dagger to the G's. OK, hopefully, yeah. It's not the most beautifully written slides or boards here. Yeah, thanks. I mean, you just want to like take the, right, so if you want to do an OR, right, like whenever this turns out to be 1, you're like, oh, definitely the real answer is 1. Whenever it turns out to be 0, you're like, well, it could be that they're all 0, or it could just be that I got unlucky. So you want to do this t times, and if you ever get a non-0 answer, you want to output 1. So sometimes you want to take the OR of your answers, which is this. Thank you. Good. All right, so let's do the analysis. I think it's going to be pretty clear, but OK, so the overall construction is proper because everything was proper all along. This thing is also proper. And for the degree, well, I mean, the worst scenario is actually the OR gates and the AND gates. It goes up by, at most, factor 2t at each gate. OK, and then for any path from the root to the from the output gate to the leads, that's of length at most d, because it's a depth d. So therefore, the degree is at most 2t to the d at the end. Yep. And let's just check the error. Hopefully it's pretty clear, but let me erase this. Okay, so what we want to do here is fix an x. Right, because our error statement is like a worst case over x, and we just want to imagine like, you know, what happens with these when we replace the gates by the polynomials for this fixed x, and just look at when an error may be introduced. You know, only the and or gates can actually introduce error. But, you know, the probability they do so is at most 2 to the minus t. So we union bound over all the gates. And, well, that's it. S times 2 to the minus t. Any questions? OK, so that's the end of the theorem 1. And that's a nice fact to know. Before going on to prove theorem 2, I just want to pause here a minute to make this theorem slightly better in a way that like has no like useful effect for the context of today's lecture, but will be useful in the future. And by that, I mean I want to look at how many random bits this polynomial uses. So it actually doesn't matter for us for the purpose of this lecture. We don't care, but we're going to care later. And we've been like very profligate with our random bits here. Like every time we encountered a gate, we're just like, yeah, let's do t times fan in many new random bits. So that could be as many as, OK, there's s gates. Fan in could be bounded by s. And then t, you know, for a corollary, right, t is going to be like log s. So that's like s squared log s random bits potentially we used, which is a lot. I just want to show you that you can actually use only polylog s bits. That's something that we'll care about later. And I won't even 100% prove it, but I'll sketch it to you. So let me call this a little exercise. OK, so first of all, let's observe that like at one gate, you know, an and or gate, we basically use fan in many random bits, just even for the basic g, and then we repeated t times. OK, we're not going to try to beat anything with the repeated t times, but we can use many fewer than fan in many random bits and still achieve basically this property. So this is where it's like really like the Valiant-Vazirani theorem. Remember the Valiant-Vazirani theorem, like what were you doing? It's not 100% the same, but like the proof, why I call it an exercise, is basically the same. Valiant-Vazirani theorem, remember, like reduced like circuit satisfiability in a random way to unique circuit satisfiability. So if you have like a circuit, it could have like any number of satisfying assignments. It's kind of like you're doing like an OR over all like 2 to the n potential strings that may satisfy the circuit. And you're probabilistically trying to like whittle that away to like exactly 1, or for Toda's theorem, having like an odd number. So that's where you use this like 2-wise universal hashing. And you know, you got some exponential savings. So this like polynomial, this randomized reduction was like polynomial time, which is like log in 2 to the n. OK, if you don't remember all that, and I didn't even recall it very well, don't worry about it too much. Let me just say, you know, instead of using, you know, R1 through RW being all uniform, if the position of the ones in this vector R1 through RW is chosen using a 2-wise universal hashing as in the Valiant-Vazirani theorem, if you can remember way back then. So like you use a pseudo-random function which like hashes the numbers 1 through W into a bit. And then like if the index hashes to 1, you're like, great, I'll put a 1 there. And if it hashes to a 0, you put a 0 there. And you can spend only basically log W, truly random bits. And you don't actually get this, that like the probability, like when the p's are non-zero, the probability that this linear form is non-zero is at least a half, but you get that it's at least like 1 over log s. This is sort of like, I don't know if you remember the basic step in like Valiant-Vazirani had like a 1 over 8n chance of hashing it to like a uniquely satisfiable circuit. It's the same thing. It's like 1 over the number of truly random bits. This is at least omega 1 over log s. Okay, so therefore, order like t times log squared s, which for our choices is like log cubed s, random bits suffice for one gate. Okay, so instead of spending like s log s random bits per gate, we can actually spend like log cubed s bits per gate. You might say, okay, that's fine, but we have to do this for all the gates, which there are as many as s. But actually, you don't. You can just reuse, the random bits at every gate. And that's fine because like the only thing we eventually did was take a union bound. So we can still do that even if like the randomness used at each gate is not independent. We didn't use that the gates computations failed independently. So the union bound is still OK. Okay, overall, P uses only polylog s random bits. It's actually nice because then like in a future scenario, think about this as like polylog n, you can like enumerate over all these random bits to like just compute whether p is more likely to be true or false using only like quasi-polynomial time or effort. Okay, but this little digression was just something we'll use later. Yeah.
Were we able to reuse the random bits in the original theorem?
Yeah.
Okay.
Yeah. It's because, okay, if you choose the r's over here not uniformly, which would require w bits, if you choose them like using like a 2-wise universal hash family instead, which only costs you log s bits, then you get almost the same scenario, except that like this probability of being wrong is at most 1 minus 1 over something like log s. Okay, so now like independently repeat this log s times to get this down to a constant, and then like another log s times to get it down to like much smaller than 1 over s. All right.
1 minus 1 over log s because I forgot. Why is 1 minus 1 over log s?
Well, that's why I didn't want to fully get into the details and why I called it an exercise. But if you go back and like kind of review, maybe I'll make it a homework problem. I don't know. If you go back and review like how you would prove such a statement, like by following the Valiant-Vazirani theorem, then you'll see that you'll only get this. At least I think. When I did it like hastily, that's what my thoughts were. Maybe you can get it something better. Okay. All right, so that's it. So last thing we have to do to complete this proof, let's say that parity requires exponential size and or not and mod 3 gate circuits of constant depth. Let's prove this theorem too, which says that parity cannot be well approximated by a polynomial unless that polynomial has degree bigger than root n. Oops. Okay. So the proof of this is like not very hard. If you've seen like a little Fourier analysis or like computing Boolean functions by polynomials, then it's relatively straightforward. Got my notes over here this time. Okay, so the proof is going to be by contradiction. Okay, so suppose that P of x does have the property that it equals sum over I going from 1 to n of xi mod 2 for at least 0.999 times 2 to the n x's. And that the degree of P is at most root n. Okay, we're going to get a contradiction. Okay, so a little trick here, just going to make the proof go down more easily, is to switch to plus or minus 1 notation. So here I'm thinking of parity as like the sum of a bunch of zeros and ones mod 2, and I'd rather think of it as the product of plus or minus 1 numbers. Okay, so I just fiddled with P a little to not really change its properties, but use plus or minus 1 notation. So let's see if I can get that right. Let P twiddle of x. This is still like, f3 to the n to f3. And I'm going to be talking about negative 1, which is also known as 2 in f3, but I'll call it negative 1. So let's see if I get this right. Let's let it be P of x1 minus 1 through xn minus 1 plus 1. And why do I do this? This has the property that if you give it a minus 1, it turns into a 1. Is that true? Yeah. And if you give it a plus 1, it turns into a 0. So P likes to take inputs which are 0 and 1. And P twiddle is going to like to take inputs that are plus or minus 1. So that's good. And then I want to fix this too. So here 0 goes to plus 1, and 1 goes to minus 1. Okay, because P also gives 0 and 1 outputs, and I would like P twiddle to take plus or minus 1 outputs. Okay, so I've just made this little affine shift. And now, well, the degree of P twiddle is actually the same as the degree of P, which is at most root n. Anyway, clearly cannot go down because you're just plugging in like linear forms for the variables. And just restating this, we get that P twiddle of x is equal to the product for I going from 1 to n of xi. Let's say for all x in a set called G, where G is a subset of plus or minus 1 to the n of large cardinality. Still, this is a subset of f3 to the n. Cardinality of G is at least 0.999 times 2 to the n. Okay. Okay, so this P twiddle hypotheses about it are basically the same as the hypotheses about P. this plus or minus 1 notation is going to be a little bit more convenient. Okay, let's consider, call it script f, the set of all functions from G to F3. And it's like almost all of the functions on F3 and variate functions, except we only, well, okay, not almost all. We only worry about inputs that are in this set G. So there's a lot of such functions. There's 3 to the cardinality of G of them. Now, every function at all from F3 to the n into F3 can be represented by a polynomial. Just interpolate. I mean, you saw this on homework 8, problem 1, among other places. Okay, so every f at all, but in particular every f in this script f is computable by some polynomial and variate polynomial. Okay, and for the purposes of computing a function f on this set G, which is a subset of plus or minus 1 to the n, there's no point in ever having a variable squared or cubed or anything. So we can assume such a polynomial never has an xi squared or an xi cubed. In other words, we can assume it's multilinear, or an xi to the 4th, etc. Because if you do your interpolation and you get some xi squared, we'll just replace that with 1. And you haven't changed the computation over G, because G is plus or minus 1, as all its inputs plus or minus 1. You can change this to an xi, because plus or minus 1 cubed is the same as plus or minus 1. You can change this to a 1, etc. Okay, so this is because G is a subset of plus or minus 1. Okay, so that's good. We have all these functions on G, and they can be computed by multilinear polynomials. Over F3. Okay, what does a multilinear polynomial look like? Well, it has potentially one term for each monomial. And a monomial is dictated by some subset of the variables. So some constant Cs, this is in F3, times this monomial. Okay, so I'm arguing that every f can be written in this way for some coefficient C sub s. And now take a look at this. What I want to argue next, actually, is that we can make the multilinear polynomial's degree not much more than n over 2. So right now, the degree of this polynomial is potentially n, because this polynomial right here could have cardinality n. So this is non-zero C sub everything, and it's degree n. But we have this funny trick, which is we know a low degree polynomial, a root n degree polynomial that computes the product of all the x's, the highest degree monomial, at least on G. So, if, let's say the cardinality of s is at most n over 2, leave it. But else, check out this trick. So what is the trick? So this thing is the same as the product over I in the complement of s, xi, times the product over everything, of xi on G, because that's a subset of plus or minus 1 to the n. Okay, the point is, if you're only concerned about plus or minus 1 inputs, then xi squared is 1. So like whenever two xi's like made together, they like cancel out. So if you like write down all the x's and then you times them by all the xi's that are not from S, then all the ones not from S cancel out, because this xi squared is 1, and it reduces you back to this. And that's cool, because this piece has degree at most n over 2, because we're only employing this trick when S has degree, or S is a size bigger than n over 2. And this piece, by assumption, has degree at most root n. Oh, because we can replace it by, we can replace it on G by p twiddle x, okay, which has degree at most root n. And therefore, this whole expression, under our assumption that we're trying to ultimately contradict, is computable by a polynomial of degree n over 2 plus root n. Okay, and so we can do this replacement whenever S is has cardinality bigger than n over 2. And therefore, we can make the polynomial representation of f have degree at most n over 2 plus root n. On G as something that looks like this, sum over sets S of cardinality at most n plus n over 2 plus root n, some other coefficient, maybe d sub s times the product of I in S xi. Is that clear? And now there are only so many polynomials of this form. The number of polynomials of this form is, well, 3 to the power of the number of such s's. Okay, I mean, you can choose all the coefficients from 0, 1, 2, however you like, but there's only so many monomials here. But on the other hand, in script f, among all these functions, there's 3 to the cardinality of G such functions. And each one of these guys can only be computing one function. So what do we conclude? We conclude that this exponent has to exceed the cardinality of G, or at least the cardinality of G. Well, let's leave that. Skip over here. This exponent, number of S, cardinality at most n over 2 plus root n, has to be at least the cardinality of G, which is no longer written here. Okay, well anyway, this thing was at least 0.999 times 2 to the n. Okay, now we're going to get a contradiction. Like now this is literally just elementary counting, and I'm going to not really do it even, but this thing is, who made that sarcastic sound? we can prove it. No, I'm kidding. I can either end earlier, or I can like torture you with like I don't know, computing the fourth moment of like a binomial random variable. It's up to you. No, this is okay. So what is this? This is literally exactly sum. So I goes from 0 to n over 2 plus root n of n choose I. Okay, I mean, if we summed over all the binomial coefficients, we get 2 to the n. But we just want to show that like if you go up to n over 2 plus root n, you don't get like practically all of them. So claim is that this sum is at most 0.99 times 2 to the n, which will give us our contradiction. And there's a variety of elementary ways to prove this fact, and I eventually chose to present none of them. I think you can I'll just convince you why it's true, and then we'll call it quits. Right, this is equal to, this is equivalent, the claim is equivalent to saying that the probability if you flip n coins that you get less than n over 2 plus root n heads is at most 0.99. So actually at least a 1% chance that you'll like go root n over the expectation. And I'll call this an exercise. I mean, the expected number of heads is, of course, n over 2. And the standard deviation of the number of heads is the square root of the variance, which is n over 4. So it's root n over 2. So this event is about going, staying at most 2 standard deviations below your expectation. OK, so this is like probability that h is at most its mean plus 2 standard deviations. OK, and we all know that like if you draw a really big binomial random variable, what you get looks like a Gaussian. This is the mean n over 2. Standard deviation is like root n over 2. And we just want to show that the probability mass here is at least 0.01. The probability that you're up here is at least 0.01. In fact, it's like a classic stats thing, right? That if you like look at either more than 2 standard deviations or less than 2 standard deviations, this is approximately, no, you never took stats. 0.95, yeah, it's like 95% chance. OK, so like this is about the probability that a Gaussian, a standard Gaussian, is at most 2, which is most the probability that a Gaussian is between 2, and that's well known to be about 0.95. OK, so it's even better. If you don't like that, you can, there's a variety of elementary ways you can check this, but I will not torture you any further. That's it for theorem 2. Any questions?
The second class inequality doesn't actually quite follow, but I guess they're both the same. Like you're limiting the range in the second one, so it should be greater than. Probably it's less than 2 is greater than 5.
Oh yeah. All right. Well.
But I think isn't that 0.95 like the probability it's at most 2 standard deviations? Yeah.
No, I don't think so. OK,
Yeah.
so good. So then we'll cross this out, and then we can put like 97.5 here, and it's still good, right? OK. Thank you. Keep me scrupulously honest. That's good. Yeah. OK, I'll see you on next Tuesday.